Somewhere in the quiet machinery of the universe, beneath the floor of everything, there may be a smallest possible piece of space. Not a small region, not a tiny grain of dust, or a single atom, or even the nucleus hidden at its center, but a smallest possible piece of space itself. A fragment of distance, below which the word distance loses its meaning. A parcel of volume so fine that nothing smaller can exist, because there is no smaller. If this is true, then the smooth and seamless space we move through every day, the space that lets a hand pass through air and a planet drift around a star, is not smooth at all. It is woven. It is built. It has a structure, the way a fabric has threads. And if a person could descend far enough, past the atoms and past the particles, past every layer of smallness the imagination can hold, they would arrive at last at the threads themselves, and find that space was never a stage on which the universe performs. Space was one of the performers all along. This is the central idea behind a theory called loop quantum gravity, and it is the quiet subject of the hours ahead. There is no need to follow every turn of it. There is no thread to lose, because losing the thread is permitted here, even expected. The words will move slowly, the way a river moves through flat country, unhurried, going somewhere, but in no rush to arrive. And if sleep comes before the river reaches the sea, that is not a failure. That is the river doing what rivers do, and the listener doing what the night asks of them. For now, only this. Far below the visible world, smaller than the smallest thing that has ever been measured, there may be a place where space comes in pieces. And the story of how human beings came to suspect such a thing is a long and gentle one, full of patient people working in quiet rooms, chalk dust settling in afternoon light, equations copied and recopied across decades. It is a story without urgency. It can be told in a low voice. It is worth saying at the very outset what kind of story this is and what kind it is not. It is not a story of certainty. No one knows whether loop quantum gravity is true. It is one of several attempts to answer a question that physics has not yet answered, and it may, in the end, turn out to be the wrong attempt. A beautiful structure built in a direction the universe did not take. That possibility is part of the texture of the thing. And rather than spoiling the story, it makes it more restful, because there is nothing here to be anxious about, nothing to get right, no examination at the end. There is only an idea, carefully built, and the slow pleasure of turning it over in the mind in the dark. If the idea is true, the listener will have spent a night in the company of the deepest structure of the world. If it is false, the listener will have spent a night in the company of one of the most careful and imaginative wrong guesses that thoughtful people have ever made. And that, too, is a fine way to spend a night, because the wrong guesses of careful people are themselves a kind of beauty, a record of the mind reaching past what it can yet grasp. So nothing in the hours ahead needs to be believed. It needs only to be heard, the way one hears rain on a roof, not as information to be retained, but as a texture, a presence, a sound that fills the room and asks nothing in return. The grains of space, if they exist, have been doing their silent work for 14 billion years without anyone's belief. They will not mind being doubted for one more night. They will not mind being slept through. They are, by their nature, the most patient things there are. To understand why anyone would propose that space is built from finite pieces, it helps to begin with two great descriptions of the world, two theories that physics inherited from the 20th century, each one magnificent, each one tested 10,000 times and never once found wanting, and each one, quietly and stubbornly, refusing to agree with the other. The first of these is general relativity. It came from Albert Einstein, finished in the autumn of 1915, and it is, before anything else, a theory about gravity. But its way of explaining gravity is unexpected, strange, and beautiful. In Einstein's description, gravity is not a force in the ordinary sense, not a pull transmitted across empty space the way a rope pulls a weight. Gravity is geometry. It is the shape of space and time themselves. A massive object, a star, a planet, a person, bends the space around it, the way a heavy stone resting on a stretched sheet creates a dip, a curved valley in the surface. And other objects, moving through that curved region, simply follow the curve. The Earth orbits the Sun not because a rope of force ties them together, but because the Sun has shaped the space nearby into a long, gentle, closed valley. And the Earth, moving freely, rolls along the inside of that valley forever, falling and never landing. In this picture, space and time are not a fixed backdrop. They are not an empty room in which events happen. They are themselves a kind of fabric, flexible, dynamic, able to stretch and bend and ripple. When two black holes collide far across the universe, they shake this fabric, and the tremor spreads outward as a wave, a ripple in the shape of space. And more than a century after Einstein wrote his equations, instruments on Earth, exquisitely still and exquisitely patient, felt one of those ripples pass through and recorded it. The fabric is real, it moves. That is the first great lesson, and it is worth resting on for a moment because everything that follows depends on it. Space isn't nothing. Space is a thing, and like all things, it can change. There is a particular phrase that physicists use for this property of Einstein's theory, and the phrase will matter later, so it can be set down gently now and left to settle. They say that general relativity is background independent. What this means is that there is no fixed stage, no pre-given grid of space and time laid down in advance, against which events are measured. In the older physics, the physics before Einstein, space and time were exactly such a stage, an absolute, unchanging framework, the same everywhere and always, within which the planets moved and the apples fell. Einstein dissolved that stage. In his theory, there is no framework separate from the things in it. The geometry of space and the matter within it determine each other, shape each other, in a single closed conversation. The fabric tells the matter how to move, and the matter tells the fabric how to curve, and there is no third thing, no external scaffolding, holding them both. This is one of the most radical features of general relativity, and it is also, as the story will show, the feature that loop quantum gravity holds onto most fiercely, the principle it refuses, under any pressure, to give up. The second great description is quantum mechanics, and it came together more slowly, assembled over the first 3 decades of the 20th century by a whole generation of physicists working in many countries and many languages. Quantum mechanics is the physics of the very small of atoms, of the particles inside them, of light itself. And its central discovery, the one that gives the theory its name, is that nature, down at its smallest scale, comes in discrete amounts, in packets, in quanta. Before quantum mechanics, it was natural to assume that the world was smooth all the way down. Energy, it seemed, could come in any amount at all, flowing and dividing as finely as one wished, the way a quantity of water seems endlessly divisible. But this turned out not to be true. Energy, in many situations, comes in steps. An electron bound to an atom cannot hold just any amount of energy. It can hold this amount or that amount, but nothing in between, and when it changes, it does not slide smoothly from one value to the next. It jumps, it is here, and then it is there, with no journey through the middle. Light, similarly, is not an infinitely divisible stream. It arrives in particles, in photons, in countable units of brightness. The world, examined closely enough, is grainy. It has the smallest size for things. It comes in pieces. The word for these smallest pieces is quanta, and it is a quiet and lovely word, and the discovery it names came reluctantly, almost against the will of the people who made it. Max Planck, at the very end of the 19th century, introduced the idea of energy in discrete packets only as a mathematical trick, a device to make a stubborn calculation come out right. And he did not, at first, believe it described anything real. He hoped for years afterward that the discreteness would somehow dissolve back into smoothness once the physics was properly understood. It did not. The graininess was real, and it deepened. And by the 1920s, it had become the foundation of an entire new physics. A physics in which the smooth and continuous picture of the world inherited from earlier centuries was quietly and permanently set aside for everything small enough to test it. The universe, it turned out, had a grain. Many of the people who discovered this were uneasy about it, but the grain did not depend on their comfort, and it has never gone away. And here is the quiet tension at the heart of this whole story. Two theories, both are correct, as far as anyone can tell. Both confirmed again and again by careful experiment. And yet they describe the world in two incompatible languages. General relativity says that space and time form a smooth, continuous, endlessly flexible fabric, curving gracefully without a break anywhere. Quantum mechanics says that nature, examined closely, is discrete, grainy, made of countable pieces, jumping rather than sliding. One theory says smooth, the other says grainy. And for most of the last century, this disagreement did not matter very much, because the two theories ruled over two different kingdoms that rarely touch. General relativity governs the large and the heavy, stars, galaxies, the universe entire. Quantum mechanics governs the small and the light, atoms, particles, the faint flicker of individual photons. A star is far too large for its quantum nature to show. An atom is far too light for its gravity to matter. So each theory works beautifully in its own domain, and the physicist, moving between domains, simply picks up one tool or the other, the way a carpenter picks up a saw for one task and a plane for the next. And the tools never quarrel because they are never used on the same piece of wood. But there are places, rare, extreme, hidden places, where the two kingdoms overlap, where something is both very heavy and very small at the same time. And in those places, the two theories must somehow be used together, and they refuse. They give nonsense. They produce, in the language of physics, infinities, answers that are not large but unbounded, not difficult but meaningless, the mathematical equivalent of a question that has dissolved before it could be asked. There are two such places, and they are among the most extraordinary locations the universe contains. The first is the center of a black hole. The second is the very beginning of the universe itself, the first instant, the moment that is usually called the Big Bang. In both places, an enormous amount of matter is squeezed into an unimaginably small volume. In both places, the heavy meets the small. And in both places, general relativity, asked to describe what happens, produces a thing called a singularity, a point where its equations report that curvature becomes infinite, that density becomes infinite, that the smooth fabric of space is not merely stretched but torn, that the description has broken down completely, and the theory is, in effect, telling its own users that it no longer knows what it is talking about. A singularity is not a discovery, it is a confession. When a physical theory produces a singularity, it is not revealing some exotic object at the center of a black hole. It is admitting a limit. It is saying, "Here at this place, I have run out of things I can truthfully tell you. Something else is needed. Some deeper theory, some more fundamental description must take over where this one fails." It can help to think of it the way one might think of a very good and very old map. Imagine a map drawn with great care, accurate across an entire continent, trusted for generations. And then imagine that, at one particular spot on the map, instead of a coastline or a mountain, there is a small region where the ink simply runs together into an unreadable blot. The blot does not mean that something monstrous and ink-colored exists at that place in the real world. It means the mapmaker's technique failed there. The territory is fine. It is the map that has a flaw. A singularity is an ink blot on the map of physics. The center of a black hole is a real place. The early universe was a real time. And the fact that general relativity produces nonsense when asked about them does not mean that nonsense is what is actually there. It means a better map is needed, a map drawn with a technique that does not blot. That deeper description, the one that would explain what truly happens where gravity and the quantum meet, has a name even though it does not yet fully exist. It is called quantum gravity. It would be a single theory, written in a single consistent language, that contains general relativity and quantum mechanics both. That reduces to one of them in the kingdom of the large and to the other in the kingdom of the small. But that remains sensible and finite and meaningful even in those rare overlapping places where the old theories collapse. Finding quantum gravity has been described by many physicists as the single most important unsolved problem in fundamental physics, the great open question that the 20th century handed to the 21st. Still unanswered, still waiting. And loop quantum gravity is one of the serious attempts at an answer. It is not the only attempt. The most famous rival is string theory, and the two approaches are different enough that it is worth, in a quiet way, marking the difference, because the contrast illuminates what loop quantum gravity actually is. String theory is, in its ambition, enormous. It tries to be a theory of everything, not only of gravity, but of every particle and every force, the whole catalog of nature unified into a single framework. To do this, it proposes that the fundamental objects of the universe are not point-like particles, but tiny vibrating strings, and that these strings move and vibrate not in the 3 dimensions of space we know, but in 9, with the extra 6 somehow curled up too small to see. It is a grand and intricate construction, and it has occupied some of the most brilliant minds of the age. Loop quantum gravity is more modest, and the modesty is deliberate. It does not try to explain every force and every particle. It does not propose extra dimensions. It does not require strings. It sets itself one task, and one task only, to find the quantum theory of gravity, to understand what space and time actually are when the quantum nature of the world is taken seriously. It begins from general relativity, from Einstein's geometric vision of gravity as the shape of space, and it asks a single, narrow, stubborn question. If space and time form a fabric, and if quantum mechanics tells us that nature comes in discrete pieces, then is the fabric itself made of pieces? Is space, at the smallest scale, grainy? The two approaches differ not only in ambition, but in temperament, and the difference is worth dwelling on for a moment, because it is genuinely a difference of philosophy and not merely of technique. String theory, in its standard form, begins by assuming a background, a stage of space and time, often with its full complement of extra dimensions, and then studies how strings move and vibrate upon that stage. It is, in this sense, a theory of objects within space. Loop quantum gravity refuses to assume a stage at all. It holds, with Einstein, to background independence, to the principle that there is no pre-given grid, that the geometry of space is itself the dynamical thing to be quantized, not a fixed arena within which other things are quantized. For the loop physicist, this is the whole point. Quantizing gravity does not mean adding gravity to a quantum theory of particles on a fixed background. It means quantizing space and time themselves, with nothing underneath them, nothing holding them up. The theory is, in the words of its founders, a genuine attempt to grasp what quantum space actually is, at the deepest level, on its own terms. Neither theory has been confirmed. Neither has produced a prediction that experiment has been able to check at the scales where they truly differ from the older physics. They are both, at present, candidate answers to the same unanswered question, pursued by different communities, presented at different conferences, written in different mathematical dialects. For a long time, the two communities barely spoke. In more recent years, there have been quiet attempts to build bridges, to find places where the methods of one might illuminate the other, and a few physicists have moved comfortably between them. But the honest situation, the one worth carrying into the night, is simply that the question of quantum gravity remains open, that more than one serious path is being walked at once, and that no one yet knows which path, if any, leads home. There is a kind of peace available in that uncertainty, too, the peace of an unfinished thing, a cathedral still under construction, with the scaffolding still up and the final shape not yet decided. For the rest of these hours, the path being walked is the loop, and the people who first set out along it worked, for the most part, quietly, far from the spotlight, and the story of how they did it is the next slow stretch of the river. The story begins, in a sense, with a frustration. By the middle of the 20th century, physicists had already tried, more than once, to combine quantum mechanics with general relativity, and the attempts had not gone well. There was an equation, written down in the 1960s, that was meant to be the quantum description of the gravitational field. It carried the names of two physicists, John Wheeler and Bryce DeWitt, and it was called the Wheeler-DeWitt equation. It was a beautiful and serious piece of work, but it was also, in practice, almost impossibly difficult to use. It resisted solution. It was, in the words of those who struggled with it, mathematically ill-behaved, and for years it sat there, a doorway that everyone could see and almost no one could pass through. John Wheeler himself, the same physicist, was a man given to vivid imagination, and he had a phrase for what he believed space might look like at the smallest scales. He called it space-time foam. His intuition was that if a person could shrink down far enough, down toward the very smallest distances physics could speak of, the smooth and placid space of everyday life would dissolve into something restless and churning and uncertain. A froth, a foam, a region where the very notions of here and there, of distance and shape, became blurred and fluctuating. It was only an intuition, a picture in the mind of a thoughtful man. He could not prove it, he could not make it precise. But it was a seed of an idea, and it would lie in the soil for a long time before anything grew from it. The first real turning point, the one that genuinely opened the door, came in the year 1986. And it came from a physicist named Abhay Ashtekar. He had been born in 1949 in India, in the state of Maharashtra, and he had studied in Bombay and then in the United States, in Texas, and in Chicago, and he had become, by the 1980s, a thoughtful and careful worker in the difficult field of gravitation. What Ashtekar did in 1986 was not to solve the problem of quantum gravity. It was something quieter and, in its way, more important. He found a new way to write down Einstein's old theory. This needs a moment of patience to appreciate, because at first, it sounds like a small and technical thing, merely rewriting equations that already existed. But in physics, the way a theory is written matters enormously. The same physical truth, expressed in two different mathematical languages, can be a locked vault in one language and an open room in the other. Einstein's general relativity had always been written in the language of the metric, a mathematical object that at every point in space and time encodes the distances and angles, the local geometry, the shape. It was the natural language for the theory, and it had served for 70 years. But it was also, for the purposes of quantum mechanics, an awkward language, full of mathematical thorns that snagged every attempt to quantize. What Ashtekar found was a different set of variables, a different mathematical vocabulary in which the very same theory of general relativity could be expressed. And in this new vocabulary, written down in a paper published in a journal called Physical Review Letters in 1986, gravity suddenly looked different. It looked, in fact, remarkably like the other theories of physics, like the theories that describe electromagnetism and the nuclear forces, the theories that physicists already knew how to quantize. Einstein's gravitational field in Ashtekar's reformulation became something very close to the kind of field that appears in those other, more tractable theories. The thorns were gone. The equations that had been so terribly tangled became, comparatively, smooth. A door that had been locked for decades quietly came unlatched. These new variables came to be called the Ashtekar variables, and the year 2026, by a quiet coincidence, marks the 40th anniversary of their introduction. They did not, by themselves, constitute a theory of quantum gravity. They were a tool, a key, a new way of holding an old problem, but the K fit, and others soon noticed. There is a further detail in how the loops first appeared, and it is a quiet example of how knowledge moves sideways through physics, an idea bred in one field crossing over to solve a problem in another. The technique that made the loops natural had been developed years earlier, in the 1970s, by a physicist named Kenneth Wilson, who was not thinking about gravity at all. He was thinking about the strong nuclear force, the force that binds the particles inside an atomic nucleus, and he had introduced a mathematical object, now called a Wilson loop, for studying that force. A Wilson loop is, roughly, a way of asking what happens to a quantity as it is carried all the way around a closed path and brought back to its starting point. The amount by which it has changed encodes information about the field through which it traveled. Wilson's loops were a tool for nuclear physics. But when Ashtekar's new variables turned gravity into something that looked like the other field theories, those same loops became the natural objects to use. And, carried over into gravity, they behaved better there than they ever had in their field of origin, precisely because gravity, written in Ashtekar's way, kept its background independence. An idea built for the nucleus found its true home in the structure of space. Among the first to notice the power of the new variables were two physicists named Ted Jacobson and Lee Smolin. They took the troublesome old Wheeler-DeWitt equation, the doorway that no one could pass through, and they rewrote it using Ashtakar's new variables, and they discovered something unexpected. The equation, recast this way, had solutions, and the solutions were labeled by loops, by closed curves in space, by rings. This is the moment the theory finds its name. Loops. Closed paths threading through space, returning to where they began. When the equation of quantum gravity was written in the new language, what emerged from it were these rings, and the rings seemed to be telling the physicists something about the structure of space itself. Lee Smolin, an American physicist, and Carlo Rovelli, an Italian one born in Verona in 1956, then took these loop solutions and, working together, did the essential thing. In 1988, building on Ashtakar's foundation, they constructed from the loops a genuine, mathematically defined quantum theory of the gravitational field. A theory that did not depend on a fixed background space. That was, in the technical phrase, background independent. And that did not rely on the approximations that had failed before. Loop quantum gravity, as a named and definite thing, was born. There is a detail in this origin story that is worth pausing on, because it is gentle and slightly surprising. When Rovelli, Smolin, and Ashtakar first found these loops emerging from their equations, they imagined, naturally enough, that the loops were small, that each loop described some infinitesimal element of space, some vanishingly tiny piece. But as they worked, as they followed the mathematics where it led, they slowly came to a different understanding. The loops were not infinitesimal, they were finite. Each loop described a finite element of space, an actual piece with an actual size. And the picture that formed in their minds, Rovelli later wrote, was of space as a sort of extremely fine fabric, woven from these loops, and that nothing at all, appeared to exist at scales smaller than the structure of the weave itself. The loops were not in space. The loops were spaced. That is the heart of loop quantum gravity, and the rest of the theory, the rest of the hours ahead, is in a sense only the patient unfolding of that single image. Space as a weave. Space as a network of finite loops. Space is not an empty container of things, but as a thing itself, made of pieces, like everything else the quantum world has ever shown us. There is one more idea from this early period worth setting down before the river moves on, because it deepens the picture, and it is, in its way, deeply restful. When the loops were understood as finite elements of space rather than infinitesimal ones, a strange and beautiful consequence followed. The loops, the founders realized, are not loops located somewhere. They are not threads sitting at particular addresses within a larger space, the way a thread of cotton sits at a particular place on a table. There is no larger space for them to sit in. The loops and the network they form are space, and so the only thing that can be said about any one loop is how it connects to the others. Its identity is entirely relational. It is defined not by where it is, because there is nowhere apart from the network, but only by what it touches, what it links to, and what it neighbors. The founders had a name for the resulting objects, the knotted, abstract quantum states of pure geometry. They sometimes called them S-knots. And the essential lesson of the name is that these states are not excitations happening in space. They are excitations of space. There is nothing underneath them. They are at the bottom. This is a thought that can be turned over slowly in the dark. Everything a person has ever known about location, here, there, near, far, this room, that distant country, is, in this picture, not fundamental. It is a pattern of relationships within the weave. Far does not mean a long stretch of pre-existing emptiness. It means many links of the network lying between one node and another. Near means few links between them. The whole vast sense of cosmic distance, the gulf between the Earth and the stars, becomes a statement about how the network is connected, about how many grains of space lie along the path. And there is something quieting in that. The distances are not voids to be crossed. They are relationships, woven, continuous, every far thing joined to every near thing by an unbroken chain of the smallest pieces. The whole universe a single connected fabric, with no true gaps anywhere in it. It is a good place to pause. The two great theories, smooth and grainy, that would not agree. The two extreme places, the black hole's center and the universe's beginning, where their disagreement turned to nonsense. The need for a deeper theory. And then the quiet sequence of insights, Wheeler's foam, Ashtakar's new variables, the loops emerging from the old equation, Ravelli and Smallin weaving them into a theory. The river has come a little way. There is no need to hold all of it. The next stretch will move more slowly still, and it will move toward the strangest and most beautiful claim the theory makes. That space can be counted, that area and volume come in smallest possible amounts, and that there is, hidden beneath the world, a smallest possible patch of existence. To approach that claim, it helps to think for a while about the idea of discreteness itself. Because it is an idea the universe has shown us before in gentler settings, and the earlier examples can make the strange new one feel less strange. Consider the matter. Consider an ordinary object, a stone, a cup of water, a length of iron. To the eye and the hand, these things seem perfectly continuous. The water pours and flows and divides without any visible limit. The iron is solid and seamless. Nothing about the everyday experience of matter suggests that it comes in pieces, and yet it does. Every one of those substances is made of atoms, discrete, countable units, with empty space between them. The water that seems so smoothly divisible cannot, in fact, be divided forever. Divide it far enough, and you reach a single molecule of water, and divide that, and it is no longer water at all, only the atoms that compose it. The smoothness was an illusion of scale. It was simply that the pieces were so small and so numerous that the eye blended them into a seamless whole, the way the separate threads of a distant fabric blend into what looks like an unbroken surface. The same is true of electric charge. Charge does not come in any amount whatsoever. It comes in multiples of the smallest unit, the charge carried by a single electron, and no isolated thing has ever been found carrying a fraction of that unit. The same is true of energy in a bound system, as quantum mechanics first revealed. The electron in an atom occupies discrete levels, discrete rungs on a ladder, and cannot rest between the rungs. Again and again, across a century of physics, the pattern has repeated. A thing that seemed smooth and continuous, examined closely enough, turned out to be discrete, to come in pieces, to have the smallest unit below which it cannot be divided. There is a quiet rhythm to this history, and it is worth letting the rhythm sound. First, it was matter, the ancient guess of the atom, confirmed at last by the patient work of the 19th and early 20th centuries, until no one could doubt that the substances of the world are built from countable particles. Then it was light, which Newton had thought a stream and the 19th century had thought a wave, and which the 20th century found to be, in its way, a hail of discrete photons. Then it was the energy of bound systems, the rungs of the atomic ladder. Then it was charged. Each time, the same surprise, softened a little by familiarity. The thing that looked like a smooth flow was a multitude of small fixed pieces, blurred together by their own number and smallness into the appearance of a continuum. The water in a glass looks like a continuous substance and is, in fact, a swarm of molecules. A beam of sunlight looks like a continuous brightness and is, in fact, a swarm of photons. The universe has a habit, when looked at closely, of turning out to be countable. Loop quantum gravity takes this long, repeated lesson and applies it to the last and most fundamental thing, to space itself. If matter is grainy, and charge is grainy, and energy is grainy, then perhaps space, the apparent container of all of them, is grainy too. Perhaps space has atoms, not atoms in space, atoms of space. And the remarkable thing, the thing that makes loop quantum gravity a genuine scientific theory rather than a poetic speculation, is that this graininess is not assumed at the start. It is not put in by hand. The theory begins, as we have seen, from general relativity rewritten in Ashtakar's variables. And then it applies the standard procedures of quantum mechanics, the same procedures that revealed the discreteness of energy in the atom. And when those procedures are carried through, the discreteness of space emerges on its own. It falls out of the mathematics, the way the discrete energy levels of the atom fell out of the mathematics, unbidden, a consequence rather than an assumption. The theory was asked a question in the language of the quantum, and the answer it gave back was, space comes in pieces. To describe how this works, the theory uses a particular mathematical structure, and the structure has a name worth saying slowly, because it will return many times in the hours ahead. The structure is called a spin network. The name has two parts, and each part can be approached gently. The word network is the easier of the two. A network, in the everyday sense, is simply a collection of points connected by lines, a web, a graph, a mesh. Think of a diagram of cities joined by roads, or of the dots and lines a child might draw. Points and the connections between them, that is all a network is. In loop quantum gravity, a spin network is exactly this kind of object, a graph, a collection of points, which physicists call nodes, joined by lines, which they call links or edges. And here is what the network represents. It does not represent objects sitting inside space. It represents space itself. Each node of the network, each point, corresponds to a small chunk of volume, a tiny grain of space, a single one of the atoms of space we have been moving toward. And each link, each line connecting two nodes, represents a surface, a small patch of area where two of those grains of volume touch one another. The network, taken as a whole, is the quantum description of a region of space. The grains of volume sit at the nodes. The patches of area connecting them sit on the links. And the entire fabric of space, in this picture, is a vast spin network, an unimaginably intricate web of nodes and links, with every node a quantum of volume and every link a quantum of contact between them. Now the other word, spin. This one is more abstract, and there is no shame in letting it remain a little abstract, because even physicists, when they use the word, do not mean spinning in the ordinary sense. Spin in quantum physics is a property that particles and fields carry, a kind of intrinsic quantity, and it comes, like so much else in the quantum world, in discrete amounts, labeled by numbers, half-integers, and integers, a quiet ladder of allowed values. In a spin network, every link is labeled by one of these spin numbers. The number on a link is not decoration. It carries the physics. It determines how much area a particular patch of surface contains. The mathematics that governs how these spin labels combine at the nodes. how the links meeting at a single grain of space must fit together in a consistent way, comes from a branch of quantum theory that was worked out long before anyone applied it to gravity, the theory of how angular momenta add together in the quantum world. The objects living at the nodes, the things that describe how the incoming links are stitched into a coherent grain of volume, are called intertwiners. And there is a beautiful way of picturing what an intertwiner is. A node of a spin network, with its links and its intertwiner, can be understood as a tiny quantum polyhedron. A small many-faced solid, like a die or a cut gem, where each face of the solid corresponds to one of the links, and the area of each face is set by the spin label on that link. And the volume enclosed by the solid is the quantum of volume that the node carries. A region of space, in this picture, is something like a vast heap of these tiny gems, each one packed against its neighbors, each shared face a patch of contact, the whole assembly an immense three-dimensional mosaic. It is not quite a literal heap of solid stones. The quantum nature of the thing makes it subtler, fuzzier, less like a fixed pile, and more like a cloud of possibilities for a pile. But the image of the mosaic, of space as a fitting together of countless tiny faceted cells, is close enough to the truth to be worth carrying into sleep. And this is where the theory makes its first, genuinely astonishing prediction. The prediction that, more than any other, deserves to be lingered over in the slow hours of the night. Because the spin labels come in discrete steps, because they form a ladder of allowed values with nothing permitted in between, the areas they determine also come in discrete steps. Area, in loop quantum gravity, is quantized. A surface cannot have just any area at all. It can have this area, or that area, or the next one up the ladder, but never a value in between. There is a smallest possible non-zero area, a smallest patch of surface that can exist, and every other area is built from steps measured against it. The same is true of volume. The nodes of the spin network, the grains of space, also carry discrete labels, and those labels determine discrete amounts of volume. There is a smallest possible chunk of space, a minimum grain, and every larger region is composed of a whole number of such grains fitted together. Space, in the deepest description loop quantum gravity can offer, is not a smooth and infinitely divisible continuum. It is countable. It is a number of pieces. It can, in principle, be tallied. It is worth noting, quietly, that the spin network was not, in the first place, invented for loop quantum gravity. The idea came earlier, from the British mathematician and physicist Roger Penrose, who had explored networks of this kind decades before, as an attempt to imagine how the smooth space of ordinary experience might be built up out of purely combinatorial pieces, out of nothing but discrete relationships, numbers, and connections, with no prior space assumed. It was a speculative idea then, a sketch, a possibility held in reserve. And when Ravelli and Smallin, in the middle 1990s, found that the quantum states of geometry in their theory were most naturally described by exactly such networks, it was a moment of two ideas, conceived separately and for different reasons, recognizing each other. Penrose's old combinatorial sketch and the loops emerging from Ashtakar's variables turned out to be the same structure, approached from two directions. The spin networks were waiting, in a sense, before the theory that needed them had been built. There is a number associated with these smallest pieces, and it is one of the most important numbers in all of physics. Its name is the Planck length. It is named for Max Planck, the German physicist who first, at the very dawn of quantum theory, noticed that certain fundamental constants of nature could be combined to produce a natural unit of length. A length built not from any human convention, not from the size of a king's foot or the circumference of the earth, but from the deep constants of the universe itself, the speed of light and the constant of gravitation and the constant that governs the quantum. When those constants are combined in the way Planck noticed, they yield a length, and the length is almost incomprehensibly small. It is worth trying, slowly and without strain, to feel how small. Write the number 1. Now imagine placing a decimal point before it, and then, between the decimal point and the 1, placing not a few zeros but 34 of them. The Planck length is roughly that about 1 part in 10 followed by 35 zeros of a meter, a distance so far below anything the senses or the instruments of human beings have ever reached that ordinary comparison fails entirely. An atom is fantastically small, far too small to see. But the Planck length is smaller than an atom by very roughly the same enormous factor that an atom is smaller than a person. If a single atom were swollen up to the size of the entire observable universe, the Planck length, blown up by that very same factor, would grow only to something like the size of a tree. The smallness is of a different order than the word small can usually carry. And this is the scale at which loop quantum gravity says the graininess of space lives. The smallest patch of area is roughly the Planck length multiplied by itself. A Planck area, a square so small that the number describing it has dozens of zeros. The smallest grain of volume is roughly the Planck length multiplied by itself 3 times, a Planck volume smaller still. To give one quiet measure of it, an ordinary sheet of paper, the kind a person might hold in one hand, has a surface so vast in these terms that to account for its area, the theory would need something like 100,000 billion 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 of the smallest possible patches, a number with roughly 68 zeros. Space is grainy, but its grains are so unspeakably fine that no microscope, no accelerator, no instrument that human beings have ever built or seriously imagined building has come anywhere close to resolving them. The weave is real, the theory says. It is simply far, far finer than sight. This is why Wheeler's old phrase, spacetime foam, returns at this point in the story. Wheeler had imagined, decades earlier, that space at the smallest scales would become a churning froth, and loop quantum gravity, when it produced its spin networks and its polymer-like, thread-like structure at the Planck scale, was seen by its founders as a mathematically precise realization of exactly that intuition. Wheeler had drawn the picture in his mind. The theory gave the picture equations. The foam, the weave, the network, different words reaching toward the same quiet idea that the floor of the world is not a smooth slab but a fine and intricate structure, and that the smoothness we know is only the structure seen from very far away. It is worth resting here, in the middle of this idea, because it is a restful idea once the strangeness softens. Every surface a person has ever seen, the surface of a lake, the surface of a hand, the surface of the moon, is, if loop quantum gravity is right, composed of a finite number of the smallest possible patches, a vast but countable tally of Planck areas. Every volume, the volume of a room, the volume of a breath, the volume of an ocean, is a finite number of the smallest possible grains. The world is enormous, and the world is made of pieces, and the pieces are so small that their smallness is itself a kind of vastness, a descent without apparent end that nonetheless does end, that bottoms out, that reaches a floor. There is a smallest size. Below it, there is nothing, not empty space, but no space, no smaller place for anything to be. the descent stops. And there is something quietly consoling in that, in the idea that the falling inward of scale is not infinite, that it arrives somewhere, that the universe, however large, is built from a definite and finite weave. Now, having reached the floor, the story can turn back upward, and consider what this strange new picture of space actually does for the theory. What problems it solves, what puzzles it eases, what it offers in exchange for asking the listener to believe something so far from ordinary experience. And the first and oldest puzzle it addresses is the one we began with, the singularity, the place where the old theory confessed its own collapse. Recall the trouble. General relativity, when asked to describe the center of a black hole or the first instant of the universe, produces infinities. It reports that density becomes unbounded, that the curvature of space climbs without limit, that the smooth fabric is not stretched but torn. And the reason it does this, the underlying mathematical reason, is precisely that general relativity assumes space is a smooth continuum, infinitely divisible, with no smallest size. If space can be divided forever, then matter can be compressed forever into a smaller and smaller and smaller volume, with no floor to stop the fall. And a quantity squeezed into a volume that shrinks towards zero produces a density that climbs toward infinity. The singularity is the direct and inevitable child of the assumption of smoothness. Assume space has no smallest size, and you have built into the foundation of your theory the machinery of its own breakdown. But loop quantum gravity does not assume smoothness. It says space has the smallest size. There is a smallest grain of volume, and matter cannot be squeezed into anything finer because there is nothing finer to be squeezed into. The floor exists, and if the floor exists, then the endless fall is impossible. The compression of matter must stop when it reaches the Planck scale, because at that scale, there is no smaller volume available, and a compression that cannot continue is a compression that halts. The infinity has nowhere to form. The singularity, the old confession of failure, simply does not arise. This consequence shows itself most beautifully in the application of the theory to the universe as a whole, to cosmology, to the question of the beginning. When the methods of loop quantum gravity are applied not to a black hole, but to the entire universe, treated in a simplified, smoothed-out, idealized way, the resulting framework is called loop quantum cosmology, and it grew, in the early years of this century, into the most developed and most studied offspring of the parent theory. Much of its early shape was given by a physicist named Martin Bojhold, and soon after, by Abhay Ashtekar himself and his collaborators, working through the opening decade of the 21st century. What loop quantum cosmology offers is a new answer to the oldest question: what happened at the beginning? In standard cosmology, built on general relativity alone, the history of the universe runs backward to a singularity, to the Big Bang, to a first moment of infinite density at which the equations fail and time itself seems to begin. There is, in that picture, no before. The question of what came before the Big Bang is not so much answered as dissolved, declared meaningless, because time itself is said to have started there. Loop quantum cosmology tells a different story, and it is a gentler one. Because the theory will not permit infinite density, because there is a smallest grain of volume and a largest possible density that matter can reach, the history of the universe, run backward, does not end at a singularity. It reaches the moment of greatest compression, the moment when density climbs to its maximum permitted value, and then, rather than tearing, rather than failing, it does something else. It rebounds. the contraction reverses and becomes an expansion. And in this picture, the Big Bang was not the beginning of everything. It was a passage. It was a bridge. There was a universe before it, a universe contracting, falling inward, growing denser, and that earlier universe, reaching the floor that loop quantum gravity provides, did not end. It bounced. This event has a name, and the name is the Big Bounce. It replaces the Big Bang as the central event of cosmic history, or rather, it reframes the Big Bang as one event in a longer story. The moment of transition, the hinge, the turning point between a contracting phase and the expanding phase that we now inhabit. The maximum density at which the bounce occurs is staggering. The calculations of loop quantum cosmology place it at a substantial fraction of the so-called Planck density, the natural maximum density built from the fundamental constants, a density so great that a single grain of it would outweigh whole worlds. But it is finite. That is the essential point. It is enormous, but it is not infinite, and because it is not infinite, the equations do not break, and time does not have to begin. It can simply continue, backward, across the bounce, into a phase of the universe that preceded our own. There is a particular mathematical texture to how this happens, and it can be described gently without any equations. In the older quantum cosmology, the one built on the troublesome Wheeler-DeWitt equation, the evolution of the universe was governed by a smooth equation, the kind that describes a quantity changing continuously. And that smooth equation, run backward, marched the universe straight into the singularity, with nothing to stop it. But in loop quantum cosmology, because space is grainy, the equation governing the universe is not smooth in the same way. It is what mathematicians call a difference equation, an equation that proceeds in discrete steps, grain by grain, rather than in a continuous flow. And a difference equation, it turns out, behaves differently near the place where the smooth equation failed. It does not march into the blot on the map. It remains well-defined. It steps right up to the moment of maximum density, and then it steps through and out the other side into the contracting universe that came before. The graininess of space, the very thing that makes the equation proceed in steps, is also the thing that lets the equation survive a passage that smooth physics could not survive. The discreteness is not only a feature of the theory, it is the rescue. It must be said clearly, in the calm and honest spirit this subject deserves, that the Big Bounce is not an established fact. It is not something that has been observed. It is a prediction of a particular theory of quantum gravity, a theory that itself remains unconfirmed, and it should be held in the mind as exactly that. As a possibility, an idea, a careful piece of mathematics that suggests one way the beginning might have gone, rather than a settled account of how it did go. Loop quantum cosmology is also, importantly, a simplified version of the full theory. To make the equations solvable, it assumes the universe is smooth, and the same in every direction, an idealization, and whether its gentle conclusions survive in the full, unsimplified theory is a question still genuinely open. The honest statement is the modest one. If loop quantum gravity is correct, and if its simplified cosmological version captures the truth, then the universe did not begin in a singularity. It bounced. Whether those two ifs hold is not yet known, and a theory that pretended otherwise would not be worth listening to. But even held modestly, as a possibility rather than a certainty, the Big Bounce is a thought worth carrying into sleep. It means the universe may not have a sharp and absolute beginning, a first moment with nothing before it. It means there may be a longer story, a universe before this one, contracting where ours expands, falling inward across unimaginable ages toward the moment of the bounce. And then our own universe blooming outward from that moment, carrying perhaps some faint and scrambled memory of what came before. The cosmos in this picture is older than the Big Bang. It did not switch on. It turned a corner. And the smallest grains of space, the atoms of the weave, were what made the corner possible, because they gave the falling universe a floor to land on, and a floor, once reached, is also a place from which to rise. The river slows here, and it is right that it should. The first great gift of loop quantum gravity has been laid out, the removal of the singularity, the replacement of the Big Bang with the Big Bounce, the suggestion of a cosmos without a sharp beginning. There is no need to carry the details. The image alone is enough, a universe contracting, reaching a floor it cannot pass, and gently turning, like a tide at its lowest ebb, beginning the long return. The second great gift of the theory has to do with black holes, and it requires turning attention from the largest thing, the universe, to the densest thing, the collapsed remnant of a star. But the underlying idea is the same, and the sameness is part of the quiet beauty of it. The same floor that catches the falling universe also catches the matter falling into a black hole. The same smallest grain of space appears in both stories. One theory, one floor, two rescues. A black hole, in the standard picture drawn by general relativity, is a region where gravity has become so strong that nothing, not even light, can escape from within a certain boundary, a boundary called the event horizon. The horizon is not a surface in the ordinary sense, not a wall of any material, but a surface of no return, a place beyond which all paths lead inward. And at the center of the black hole, deep inside the horizon, general relativity again places a singularity, a point of infinite density, where the collapsed matter of the dead star has, according to the old equations, been crushed out of existence into a location of zero size and unbounded curvature. It is the same confession as before, the same admission of failure, hidden now at the heart of every black hole in the universe. Loop quantum gravity, with its floor, its smallest grain, does to the black hole's center what loop quantum cosmology did to the Big Bang. It forbids the infinite compression. The matter of the collapsing star, falling inward, cannot be crushed past the Planck scale, because there is no finer scale to be crushed into. And so, instead of a singularity, the theory suggests something else at the center, a region of maximum but finite density, a place where the collapse halts, and, as in the cosmological case, may even reverse. Some physicists working in this area, Carlo Rovelli among them, have developed this idea into one of the most striking scenarios in modern theoretical physics. They have given the central object a name. They call it a Planck star, a core of matter compressed to the Planck density and held there by the discreteness of space, by the refusal of the grains to be packed any tighter. And around this idea has grown a larger and stranger picture of what a black hole, over an immense span of time, might actually be. To approach it gently, recall a discovery made by Stephen Hawking in the 1970s, that black holes are not perfectly black, that they very slowly leak energy, radiating it away over time in a faint quantum glow now called Hawking radiation. The radiation is unimaginably feeble for any black hole of ordinary size, and the time required for a black hole to lose a significant fraction of itself this way is far, far longer than the present age of the universe. But over such immense stretches of time, the black hole shrinks. Its horizon contracts. It evaporates. The scenario that some loop quantum gravity researchers have proposed picks up the story at the end of that almost endless shrinking. As the horizon contracts toward the Planck scale, they suggest, a quantum transition occurs. The matter that has been held at the center, at the Planck star, the matter that could fall no further, finally rebounds, and the black hole turns, through a quantum process, into its strange opposite. Where a black hole is a region from which nothing can escape, its opposite is a region from which nothing can enter and into which things can only emerge. And such an object is called a white hole. In this picture, a black hole is not a permanent grave. It is one phase of a much longer process. A bounce, again, the same bounce, the same turning at a floor, and the matter and energy that fell in across the black hole's long life are not destroyed, but eventually released, emerging from the white hole into which the black hole has transformed. There is a beautiful subtlety in the timing of this, ode to relativity's strange treatment of time. The whole transition, the whole bounce from black hole to white hole, might take only a very short time as measured by an imaginary clock falling along with the matter at the center. A matter of microseconds, perhaps. But because time near such intense gravity runs so differently from time far away, that brief inner process, seen from the outside, from the calm vantage of a distant observer, would be stretched across an almost inconceivable duration. Billions upon billions of years. A black hole, in this view, is a star caught in the act of bouncing, but bouncing in such extreme slow motion that, from outside, the bounce appears to take longer than the current age of the cosmos. The black holes we observe would simply be bounces we have not yet seen in their entirety. This, too, and the honesty matters here as much as anywhere, is not an established fact. The Planck star, the black hole to white hole transition, the white hole remnant. These are theoretical proposals developed within loop quantum gravity, intensely interesting and intensely debated, but not confirmed by any observation. They represent one possible answer to deep puzzles about what black holes truly are and what becomes of the matter and information that falls into them. They should be carried in the mind the way the Big Bounce is carried, as a serious and careful idea about how things might be offered by a serious theory, and awaiting the verdict that only evidence can give. A great deal of the work in this corner of physics consists precisely of trying to make these ideas sharp enough and precise enough that the universe might one day be asked whether they are true. There is, however, one place where loop quantum gravity's treatment of black holes connects to something already firmly known, and it is worth telling because it is one of the theory's quiet triumphs. It concerns the entropy of a black hole. Entropy is, in one of its meanings, a measure of hidden information, a count, roughly speaking, of the number of distinct microscopic arrangements that all look the same from the outside. A glass of water has enormous entropy because there are countless ways the individual molecules could be arranged, while the water as a whole looks identical. In the 1970s, working from general relativity and quantum theory together, Jacob Bekenstein and Stephen Hawking discovered something unexpected and profound: that a black hole has an entropy, and that this entropy is proportional not to the black hole's volume, as one might naively expect, but to the area of its horizon. The amount of hidden information in a black hole is written, somehow, on its surface, and it is measured in units of the Planck area, the very same smallest patch of area that loop quantum gravity predicts. This was a strange and suggestive result. It hinted that a black hole's horizon was somehow composed of a vast number of tiny pieces, each one a Planck-sized patch, and that the entropy was simply a count of those pieces and the ways they could be configured. But it was, for a long time, only a hint. The formula was known. The deeper reason for it, the actual microscopic picture that would explain why the entropy took exactly that value, was missing. Loop quantum gravity supplied a candidate for that missing picture, and supplied it in a way that flowed naturally from the theory's own structure. Recall that in loop quantum gravity, a surface is pierced by the links of a spin network, and each piercing contributes a discrete quantum of area. The horizon of a black hole is a surface, and so it too is pierced by spin network links, each puncture contributing its quantum of area, each puncture a small piece of the horizon. And the entropy of the black hole, in this picture, becomes exactly what Bekenstein and Hawking's formula suggested it should be. A count of the ways the spin network can pierce the horizon, a tally of the microscopic configurations of the quantum geometry at the surface. The theory could, from its own first principles, from its own atoms of space, derive the fact that black hole entropy is proportional to horizon area. The hint became, within the theory, an explanation. The picture this gives of a black hole's horizon is worth holding for a moment, because it is vivid and strange and quiet all at once. The horizon, in this view, is not a smooth, featureless sphere. It is a surface dappled with punctures, countless tiny points where the threads of the surrounding spin network pass through it, each puncture carrying its small quantum of area, each one able to take on a few different quantum values. The total area of the horizon is the sum of all these small contributions. And the entropy, the hidden information, is a measure of how many different ways the punctures could be arranged and labeled, while still adding up to the same total area. A black hole, examined this closely, is something like a vast page covered in a microscopic script. And the entropy is the number of distinct texts that could be written on that page while leaving its size unchanged. The information is not lost inside the black hole. It is written on the skin of it, in the language of the punctures, in a script far too fine for any eye. There is an honest wrinkle in this success, and the pedantic and careful spirit of this subject requires that it be told. The counting, carried out in loop quantum gravity, gives an entropy proportional to the horizon area. That much emerges cleanly and beautifully. But to make the result match the Bekenstein-Hawking formula exactly, with the correct numerical factor, and not merely the correct proportionality, the theory must fix the value of a particular number. This number is called the Barbero-Amiasi parameter, after the physicists Fernando Barbero and Giorgio Amiasi, and it entered the theory for technical reasons connected to Ashtakar's variables. The theory does not, on its own, predict the value of this parameter. Instead, physicists fix its value by demanding that the black hole entropy come out right, by tuning it until the loop calculation matches the known formula. Now there is something genuinely satisfying even in this, because the tuning only has to be done once. Adjust the parameter so that the entropy of one kind of black hole comes out correct, and then, without any further adjustment, the theory gives the correct entropy for every black hole, of every size and kind. That consistency is a real and non-trivial check. A wrong theory would not generally pass it. But the need to fix the parameter by hand, rather than predict it, is widely felt within the field to be unsatisfying, a loose thread. And the true physical meaning of the Barbero-Amiasi parameter remains, in the words of those who study it, one of the genuinely open questions of the theory. It is mentioned here not to undermine the achievement, but because honesty about the loose threads is part of what makes a theory trustworthy, and because a sleep story about science should be as truthful in its hesitations as in its wonders. The river has now passed through the theory's two great landscapes, the beginning of the universe and the interior of black holes, and in both, it has found the same gift, the same smallest grain of space catching what would otherwise fall forever. It is worth, before the night deepens further, turning attention to the people and the texture of the work itself, because loop quantum gravity is not only a set of ideas. It is a human enterprise, carried on by a few hundred people scattered across perhaps 30 research groups around the world, and there is a quiet pleasure in picturing the work as something done by particular individuals in particular places over long and patient years. Carlo Rovelli, one of the founders, became, over time, not only a physicist but a writer, and his books carried the strange ideas of quantum gravity to readers far outside the world of physics, in many languages. He worked in Italy, and then for a decade in the United States at the University of Pittsburgh, and then for many years in France, in Marseille, where he directed a research group devoted to gravity. He has written and thought a great deal about the nature of time, and one of the deepest and most disorienting suggestions to come out of loop quantum gravity is bound up with his work on that question. The suggestion that at the most fundamental level, in the basic equations of the theory, time, as we know it, does not appear at all. The equations describe the relations among things, the way pieces of the world connect to other pieces, but they do not contain a flowing time, an external clock ticking in the background. Time, in this view, is not fundamental. It is something that emerges, a feature of the world as we experience it at our large and warm and slow scale, but not a feature written into the deepest layer. The ticking is real, but it is not the floor of things. Below the ticking, the equations are still. Abhay Ashtekar, whose new variables opened the door in 1986, spent the heart of his career at Pennsylvania State University in the United States, where he held a named chair and helped build a center for the study of gravitation and the cosmos. He continued, decade after decade, to work on the theory he had helped to seed, and on its cosmological offspring, the loop quantum cosmology that produced the Big Bounce. Lee Smolin, the third of the early founders, worked for many years at the Perimeter Institute in Canada, a place built specifically to give theoretical physicists the quiet and the freedom to think about the hardest questions. And he became, over time, a thoughtful and sometimes critical voice within the whole enterprise of fundamental physics, writing about its sociology, its struggles, its need to keep more than one path open at once. And there have been many others, Thomas Thiemann, who worked to make the dynamics of the theory mathematically precise, Martin Bajhold, who did much to build loop quantum cosmology, John Baez, who helped clarify the mathematics of spin networks and spin foams, and a long roll of others in Germany and France, and the United States and India and beyond, each adding a careful piece to a structure that no single person could build alone. It is worth picturing them, not as heroes in a drama, because this subject has no drama, but as quiet workers, filling chalkboards and notebooks, attending small conferences, reading one another's papers slowly, disagreeing courteously, returning the next morning to the same difficult equations. The theory grew the way a coral reef grows, slowly, by accretion, by the patient deposit of small contributions over decades, with no single moment of triumph, only the gradual thickening of a structure. There is something worth admiring in a field that proceeds this way. Loop quantum gravity has never had a moment of glory, no headline, no prize ceremony, no experiment that suddenly proved it right and made its founders famous overnight. It has had, instead, 40 years of steady, careful, mostly anonymous work, carried on by a few hundred people who chose to spend their working lives on a problem that might not be solved within those lives, and who knew that when they began. They write papers that perhaps a few hundred other people will ever read closely. They check each other's mathematics with a patience that has no audience. They hold their own theory to a high and unforgiving standard. And some of the sharpest criticism of loop quantum gravity has come from within the field itself, from physicists who believe in the project and precisely for that reason refuse to let its difficulties be glossed over. There is a kind of quiet dignity in that, in the willingness to work hard and honestly on something slow, something uncertain, something that asks for a lifetime and promises nothing. It is the same dignity, in a way, that belongs to the grains of space themselves, patient, unglamorous, doing the work without applause. That structure, the theory itself, eventually grew a second branch, and the second branch is worth describing because it gives a fuller sense of what loop quantum gravity has become. The original approach, the one descending directly from Ashtekar and from Ravelli and Smallness' work of 1988, is called canonical loop quantum gravity. It works roughly by taking a slice of space at a single moment, and describing the quantum geometry of that slice with a spin network, and then asking how that geometry evolves. It is the older and more traditional branch. The second branch is newer, and it is called the spin foam approach, or covariant loop quantum gravity, and it took its mature shape over the opening decade of this century. The idea behind it is gentle and visual. If a spin network is the quantum description of space at one moment, a web of nodes and links, frozen, then what happens when that web evolves, when the geometry of space changes from one moment to the next? The links of the network sweep out surfaces. The nodes sweep out lines. The whole network, evolving through time, traces out a higher structure, a kind of four-dimensional history, and that structure is called a spin foam. A spin foam is to a spin network what a soap foam is to the soap films that compose it. A structure of faces and edges and vertices, a frozen record of a spin network's entire history, its evolution captured all at once. The spin foam approach offers a different way of calculating, a way more like the path integral methods that physicists use elsewhere. A way of summing over all the possible histories, all the possible spin foams that could connect an earlier state of space to a later one. The two branches, the canonical and the covariant, are believed to be two descriptions of the same underlying theory, two languages for the same physics, useful for different kinds of calculation. The way the same landscape can be described both by a map and by a photograph. Much of the most active research in loop quantum gravity in recent years has flowed through the spin foam channel, and much of it has been extraordinarily demanding. The calculations involve sums over vast numbers of configurations, and even with powerful computers, they have resisted easy completion. Only in the most recent years, with new computational methods and even the application of machine learning, have some of the harder spin foam calculations begun to come within reach. The theory, 40 years after Ashtekar's variables, is still being built, still being worked out, still revealing what it actually says. It is worth dwelling for a quiet moment on what a spin foam actually is, because the image is one of the loveliest the theory offers. Picture again a spin network, the web of nodes and links that describes space at one instant. Now let that web change. Let it evolve the way space evolves. A link might split, a node might appear, the connections might rearrange themselves. As the network changes, trace out everything it does. The links, sweeping through the change, trace out surfaces, little sheets, faces. The nodes, moving and transforming, trace out edges and meeting points. The result, when the whole evolution is laid out at once and viewed as a single completed object, is a structure built of faces and edges and vertices. And that structure is the spin foam. It is the history of a piece of space, frozen, made visible all at once. The way a long-exposure photograph of a moving thing captures the whole of its motion in a single still image. A spin network is a space at a moment. A spin foam is space across a stretch of its history, a four-dimensional record of how the weave rewove itself. And the deepest equations of the covariant theory are, in essence, instructions for adding up all the possible such histories, all the ways the weave might get from one configuration to another, and asking which way is most likely. The universe's evolution, in this telling, is a vast, quiet sum over every possible history of the fabric of space. And that brings the story to the hardest and most honest part, the part that a careful telling cannot leave out, even in the soft hours of the night, perhaps especially then, because the honest acknowledgement of what is not known is itself a kind of peace. Loop quantum gravity, for all its beauty, for all its 40 years of patient development, has not been confirmed. It is not, at present, an established description of nature. It is a candidate, a serious, well-developed, mathematically careful candidate, but a candidate still. There are two great difficulties, and they should be named plainly. The first is the problem of the classical limit. Any correct theory of quantum gravity must do more than describe the Planck scale. It must also explain why, when we step back to the large and ordinary scales of stars and planets and falling apples, the familiar smooth space of general relativity reappears. The graininess must blur, at large scales, back into the seamless fabric Einstein described, the way the separate threads of a fabric blur, at a distance, into an unbroken surface. Showing rigorously and completely that loop quantum gravity does this. That ordinary, smooth, classical general relativity emerges correctly from the underlying weave of spin networks, has proven genuinely difficult, and it remains, in the fully general case, not entirely settled. The theory builds the grains beautifully, showing in full detail that the grains, assembled and viewed from afar, reproduce exactly the world we know is harder, and the work continues. It is a subtle kind of difficulty, and it is worth understanding why it is hard, because the difficulty is itself instructive. It is one thing to write down the rules for the smallest pieces. It is quite another to prove that an enormous number of those pieces, fitted together according to those rules, will behave collectively the way the smooth theory demands. The same kind of challenge appears elsewhere in physics. It is, in a sense, easy to know the rules governing a single molecule of water and still find it formidably hard to derive, from those rules alone, the gentle flow of a river or the shape of a wave. The collective behavior of many pieces is its own deep problem, separate from the rules for one piece. Loop quantum gravity has its rules for the grains. The bridge from the grains to the smooth river of Einstein's space is still, in places, under construction, some spans of it complete and solid, others not yet finished. This is not a hidden embarrassment. It is openly acknowledged within the field, named as one of the central open problems worked on steadily. A theory that knows precisely where its own bridge is unfinished is, in its honesty, more trustworthy than one that pretends the bridge is whole. The second great difficulty is the one that hangs over every theory of quantum gravity, loop and string, and all the others alike. And it is the absence of experimental confirmation. The reason is the very smallness we dwelt on earlier. The Planck scale is so far below anything that any instrument can reach that the direct effects of quantum gravity are, with present technology, essentially invisible. To probe a distance, physics generally needs energy and more energy for smaller distances. And the energy required to directly probe the Planck length is so enormous that it lies far, far beyond the reach of any particle accelerator that human beings have built or could realistically build. The graininess of space, if it exists, is hidden behind a wall of inaccessibility, and no theory of quantum gravity has yet been confirmed by direct experiment, because no experiment has yet been able to look. Physicists have not given up on the search for evidence, and the search itself is a quiet and ingenious thing. One idea, explored over the past few decades, is that if space is grainy, then light of different energies might travel across it at very slightly different speeds, an effect far too small to notice over ordinary distances, but one that might, just possibly, accumulate into a detectable difference over the billions of years that light from a distant cosmic explosion spends crossing the universe. Astronomers have looked, in the light of distant gamma-ray bursts, for exactly this kind of energy-dependent delay. So far, the observations have not revealed it. Instead, they have placed limits, telling physicists that if the effect exists at all, it must be smaller than such and such, which is itself useful, because it constrains the theories, narrows the possibilities, tells the builders something about what their structures must look like. Other searches look to the cosmic microwave background, the faint afterglow of the early universe, for some subtle imprint that a big bounce might have left. Still others examine, in careful detail, the orbits of the planets and the bending of light near the sun, asking whether the tiny corrections that a quantum theory of gravity might introduce could be hiding just below the threshold of what the most precise measurements can currently see. This last kind of search has become, in very recent years, surprisingly active. Physicists have taken simplified models of a black hole as loop quantum gravity might describe it, with the singularity at its center smoothed away. And they have asked what such a model would predict for the gentle, well-measured effects of gravity within our own solar system. The slow turning of the orbit of Mercury, the bending of distant quasar light as it grazes the edge of the sun, the tiny delay imparted to a radio signal passing near a massive body. These effects have all been measured by spacecraft and by radio telescopes with great precision, and they all agree with ordinary general relativity to a remarkable degree. So the strategy is to ask, how large could a quantum gravity correction be and still hide beneath the precision of those measurements? The answer, worked out in studies published over the past year or two, is that any such correction must be very small indeed. And that, again, is a real result. It does not confirm the theory, but it disciplines it. It tells the builders of loop quantum gravity that whatever their theory predicts for these gentle, accessible regimes, the prediction must be quiet enough not to have been noticed yet. Each such limit is a fence placed around the space of possibilities, and the fences, slowly, are drawing the possibilities inward. None of these searches has yet found the signal, but the fact that they can be designed and carried out at all is significant, and it marks a real difference between loop quantum gravity and a mere philosophy. The theory makes claims about the world, that area is quantized, that there is a smallest length, that the Big Bang was a bounce. And claims about the world are, at least in principle, the kind of thing the world can be asked to confirm or deny. The asking is hard. The instruments are not yet sharp enough. But the questions are real questions, and a theory that poses real questions, even unanswered ones, is doing the work that science asks of it. It is worth, as the night deepens, holding both halves of this honestly and together. On one side, loop quantum gravity is a genuine achievement, a mathematically well-defined theory built carefully over 4 decades that takes Einstein's vision of space as a dynamical fabric and quantum theory's lesson of discreteness, and weaves them into a single picture in which space itself is granular, in which the singularities of the old physics are healed, in which the beginning of the universe becomes a bounce, and the center of a black hole becomes a Planck star. On the other side, it is unconfirmed, incomplete, still wrestling with how to recover the smooth world we know, still waiting for any experiment to reach the depth at which its predictions live. Both things are true. The theory is beautiful, and the theory is unproven, and there is no contradiction in saying both. Only the ordinary, honest condition of science working at the edge of what can be known. Let the river slow now, and let the remaining time be spent not on new facts, but on returning gently over the ground already crossed, the way a person drifting towards sleep returns over the events of a quiet day, not to study them, but simply to let them settle. There were 2 great theories. General relativity, which says that gravity is the shape of space and time, that the fabric of the world is smooth and flexible and dynamic, bending around every star, rippling when great masses move. And quantum mechanics, which says that nature, looked at closely, comes in discrete pieces, in countable quanta, that energy, charge, and light arrive in the smallest units rather than smooth streams. 2 theories, each magnificent, each confirmed 10,000 times, and each quietly contradicting the other, one saying smooth, the other saying grainy. For most purposes, the contradiction could be ignored, because the 2 theories ruled separate kingdoms, the large and the small, and rarely was anything both large enough and small enough to need them both at once. But there were 2 places where the kingdoms overlapped, the center of a black hole, and the first instant of the universe. And in those places, the old physics failed, produced infinities, produced singularities, confessed that a deeper theory was needed. That deeper theory, the theory of quantum gravity, has been the great unfinished task handed down to the present age. Loop quantum gravity is one attempt at it, a modest attempt, in the sense that it tries only to quantize gravity, not to explain every force and particle, and a bold one in the sense that it asks whether space itself, the apparent container of all things, is made of pieces. It began with Abhay Ashtekar, who in 1986 found a new way to write Einstein's theory, a way that made the locked door of quantum gravity swing open. It continued with Ted Jacobson and Lee Smolin, who found that the old equations, rewritten, gave solutions shaped like loops. And with Carlo Rovelli and Smolin, who in 1988 wove those loops into a genuine theory. And with the slow realization that the loops were not tiny but finite, that they did not sit in space but composed it. That space was a weave. The mathematics of the weave is the spin network, a graph of nodes and links, where each node is a grain of volume, and each link a patch of area where grains touch, and where the discreteness of the quantum labels forces area and volume themselves to be discrete, to come in smallest possible amounts, measured against the almost inconceivably tiny Planck length, a distance so far below the reach of any instrument that its smallness is itself a kind of vastness. Space in this picture is countable. Every surface is a finite tally of the smallest patches. Every volume is a finite number of the smallest grains. There is a floor to smallness. The descent inward ends somewhere. It is worth letting that settle once more slowly, the way one settles a pillow in the dark. For all of human history, the imagination has been free to fall inward without limit, to picture, inside every small thing, a smaller thing, and inside that, a smaller still, an endless descent, a smallness without a bottom. It is a slightly vertiginous freedom, that endless fall. Loop quantum gravity quietly takes it away and replaces it with something steadier. The fall inward, the theory says, is not endless. It stops. There is a smallest grain, a final floor, a last and least piece of space below which there is no smaller place for anything to be, not empty space, but no space, the simple end of the descent. And rather than being a loss, that ending is a kind of comfort. The universe is not a bottomless thing. It is built from a definite weave of a definite fineness, and the weave, however vast, is finite in its grain. There is a bottom. One can rest on it. Everything rests on it. And because the descent ends, because there is a smallest grain, the old infinities cannot form. Matter cannot be crushed past the Planck scale, for there is no finer scale to be crushed into. So at the beginning of the universe, the singularity of the Big Bang is replaced, in loop quantum cosmology, by a big bounce, a moment of greatest but finite density, a turning point, with perhaps a whole earlier universe contracting toward it from the far side. And at the center of a black hole, the singularity is replaced by a Planck star, a core of matter held by the stubbornness of the grains, and the black hole itself becomes, over almost endless ages, perhaps one phase of a slow bounce into its strange opposite, a white hole, releasing at last what it once swallowed. And the entropy of a black hole, the hidden information written on its horizon, becomes a count of the ways the spin network pierces that surface. A fact the old physics could only describe, and the new one can begin to explain. These are the gifts the theory offers. And against them stand the honest limits, that no experiment has yet reached the Planck scale to confirm any of it, that the theory still labors to show, in full rigor, how the smooth space of ordinary experience emerges from the underlying weave, that certain numbers, like the Barberouximiezi parameter, must still be fixed by hand rather than predicted, that the big bounce and the Planck star, beautiful as they are, remain proposals rather than established facts. The theory is a candidate. It is one of the serious candidates. It is not the answer, not yet, and it may never be. That too is part of the honest telling, that a theory can be beautiful and careful, and the work of 4 decades, and still, in the end, turn out not to be the way the universe is built. Science holds its candidates lightly. It waits for the world to speak. But there is something in the central image that survives whatever the verdict turns out to be, something worth carrying down into sleep regardless of whether loop quantum gravity is ever confirmed. It is the image of space as a thing, not as emptiness, not as a featureless stage on which the real drama of matter and light plays out, but as a participant, a structure, a fabric with its own deep architecture. Whatever the final theory of quantum gravity turns out to be, The long history of physics makes one thing likely: that space, examined closely enough, will not be the simple, smooth nothing that it appears to be. It will have a structure. It will have a story. The floor of the world is not a void. It is built of something. And if loop quantum gravity is right, then it is built of this, of a vast and silent network, finer than any sight, in which countless smallest grains of volume are joined to one another across countless smallest patches of area, the whole immeasurable weave shifting and reconnecting in ways that have no need of time to flow. Because time itself is only something that emerges at the large, warm scale where creatures like us happen to live, from the still and timeless relations underneath. That last thought deserves a slow and final unfolding, because it is, of all the strange suggestions the theory makes, perhaps the gentlest and the most consoling. In the deepest equations of loop quantum gravity, as Carlo Rovelli and others have long emphasized, there is no time. Not a short time, not a slow time, no time at all, no flowing parameter ticking in the background, no universal clock. The fundamental description is of relationships, of how the pieces of the world connect to other pieces, of the network and its weave. Time, the sense of one moment giving way to the next, of a past behind and a future ahead, is not written into that deepest layer. It emerges higher up. It is a feature of the world as experienced by large, warm, slow things made of enormous numbers of grains, things that remember and anticipate, things for which the weave appears to flow. The flow is real at the scale of a life. It is simply not real at the scale of the grains. Underneath the ticking, the equations are perfectly still. There is rest in that. The restlessness of time, the pressure of the next thing, the weight of the last thing, the sense of being carried forward, whether one wishes it or not, is, in this picture, not a property of the bottom of the world. The bottom of the world does not hurry. It does not age. It simply is a vast, quiet structure of relationships, complete in itself, and the hurrying is something that happens only far above it, in the warm, shallow layer where minds and clocks and days exist. And tonight, drifting down toward sleep, a person is drifting, in a sense, in the direction of that stillness, letting go of the next thing and the last thing, loosening the grip on the flow, settling toward the quiet structure underneath. Sleep is not a small thing in this light. It is a nightly return by every creature that sleeps toward the timeless layer from which the day was only ever a brief, warm pattern. Consider, as the last slow thought of this long descent, the space in the room where this is being heard. It seems empty. It seems like something simple, the ordinary air and the ordinary distance between one wall and another. But if the theory of the loops is right, then that quiet emptiness is not empty and not simple. It is a weave. Every cubic inch of it is an immense number of the smallest possible grains of space, each one joined to its neighbors, the whole thing a network so fine that all the instruments ever built could not resolve a single thread of it. The stillness of the room is the stillness of that network. The space that lets a breath move, that holds the distance between a hand and the ceiling, that separates the listener from the farthest star, all of it, the same weave, the same countless grains, the same patient architecture running unbroken from here to the edge of everything. And the same weave, run backward through the deep past, does not end at a sharp beginning. It bends, it bounces. It turns at a floor it cannot pass, the way a tide turns at its lowest reach and rises again. The universe in this telling did not switch on out of nothing. It turned a corner. It is older than its beginning. And the smallest grains of space, the very things that make the corner possible, the floor that catches the falling cosmos, are the same grains that, even now, even here, compose the quiet dark of the room and the soft distance through which sleep is, by now, beginning to arrive. There is no more thread to follow. There was never a thread that needed following. The river has reached the flat country near the sea, where it moves so slowly that it is hard to say it moves at all, and the only thing left is the slow turning, the long time, the silence between the grains. Rest now. The weave will hold. It has held the whole universe, across an age longer than its own beginning, and it will hold the small, still space of this one room through one short night without the least difficulty. The way it holds everything, quietly, completely, and without ever once being asked. If these slow hours have been a good companion for the descent into sleep, the channel offers many more like them. And a gentle press of the subscribe button means another will be waiting on another night, whenever the dark needs a quiet voice to fill it. Until then, sleep well, and let the smallest grains of space keep their patient watch.